Let's talk about parametric curves. In this video, I'm going to do two different parametric curve sketches. The first one you can see on the screen here, 3 cosine and 5 sine. And then the second example I'll do in this video is x equals t squared, y equals t cubed. And I've paired these together because they're a nice contrast of the two different techniques that we can use to sketch these parametric curves. Okay, so for this first example, you'll notice that x is attached to a cosine, y is attached to a sine. So we're going to kind of lean on our existing knowledge of the unit circle. We know that if it was just cosine and just sine here, we would be sketching out the unit circle kind of in this order, around and around and around. Looking at the ranges on t, this is kind of an imposed restriction on the values of t. So we're only using pi over 2 to 3 pi over 2. So that would be from right here all the way down to right here. Now, having the times 3 in the x equation just stretches out the x values. So instead of your x values going from -1 to 1, we're going to stretch from -3 to 3. And then something similar happens for the y's. Because we have this times 5 here, our y values, instead of coming out -1 to 1 vertically, we're going to stretch -5 to 5. That already gives us a really good sense of what we're about to sketch. Before I do that though, I'm just going to eliminate the parameter in this case. Sometimes we don't need to do this to do the sketch, but it's always good practice. So if we want to eliminate the parameter, that's the fancy phrasing that means write an equation that just involves x and y that cuts out the t value here. And the information that it gives us is kind of like the total path of the parametric curve without any direction or speed factored in. Typically, such as in the next example here, to eliminate the parameter, we'll solve one of these equations for t and then plug that into the other equation. When we have sine and cosine running around, it's typically easier to take advantage of the fact that cosine squared plus sine squared equals 1. So because we know this is true, cosine is actually x over 3. And sine will be equal to y over 5. So this is the equation that gives the full path of this parametric curve with no restrictions on t, no indication of timing and how it's actually built. You may recognize this equation or you may not, depending on how long ago you studied. This is called an ellipse. So an ellipse is the fancy math term for an oval. So this 3 tells us the x's go as y as -3 to +3, and then the y over 5 tells you -5 to 5. So we'll combine this with the thinking that we had at the beginning, which is tracing out our curve this way to match those restrictions there. You'll go as far as 5, as well as -5, and we'll also put in some direction. So we're going to trace out our oval this way, and it's going to have fairly even speed the whole way. If we didn't have these restrictions on t, we would complete this oval shape all the way around, and that direction would just kind of continue forever as a flow. In the next example, we don't have any sines and cosines to rely on. So this one we're going to have to do kind of from scratch. One thing that's worth noticing before we do anything else is that just from these equations, because x is t squared, that's only going to output positive numbers. So I can tell all my x values will be 0 or higher. So that means I'm only on the right-hand side of the x vector. Whereas y equals t cubed will output negative and positive numbers. So I know I'm going to vertically be above and below the x-axis. So we're going to graph entirely over here. Okay. So if we want to eliminate the parameter in this case, just to get a sense of the path that this will trace out, we'll do this kind of the more traditional way, which is take one of these equations and solve it for t, then plug that in for t in the other formula. If we want to have y equals a function of x, we'll solve x equals t squared for t, so you have plus or minus square root of x is t. And then we'll plug that in for t here. So we have y equals a stand-in for t cubed. This is a little awkward with the plus or minus. It just kind of stays there because the cube won't change the plus or minus. So we might call this x to the 3 halves with the plus or minus. So a graph like that, if it was just y equals x to the 3 halves, I would say, it's something between y equals x and y equals x squared, which is going to kind of be like that with a little bit of a bend. With this plus or minus up front, we just also have the near the image down here. So we're going to have something roughly like that, but from this eliminated parameter formula, we have no sense of like how this is being traced out, whether it's in one direction or the other or skewed in. So to fill in the rest of that information, what we'll do here is make a TXY chart. And again, that's kind of a more traditional way to do it. It would have also helped in this first example here, but we had some extra information that helped us bypass it. Here, I don't have a good sense of how this would be traced out, so I'm going to do a whole chart. So T, X, and Y. There are absolutely no restrictions on T here, so we're assuming T is all numbers ever, so negatives, positives. My backup numbers that I plug in for T are typically -2 to +2, just the integers. That's just kind of my go-to numbers. If other numbers look more convenient to plug in, you can switch to those. Okay, so when T is -2, X is that number squared, so that's 4. And then Y is that number cubed, which would be -3. And when T is -1, that number squared is +1, that number cubed is negative. At 0, X and Y both come to 0. At 1, we have 1 squared and 1 cubed are both 1. And then finally, when T is 2, X is 2 squared, which is 4. And then Y is 2 cubed, which is +3. So now I'm going to take just the XY portion and plot these points on my graph here and plot them in order. So I'm going to label them with what T value they came with, so that it'll be this one, then this one, then this one, and that's how we get a sense of like the order in which it's being traced out. Okay, so the first one up is 4 -8 into 4, and then we'll go all the way into -8, and I'll label this. This is the T equals -2 point. All right, the next one up is 1 -1. That's all the way up here. At 0, we're at 0 squared. That's the T equals 0 point. So I can tell from this kind of initial image, it looks almost straight here, but I know it was going to be a little bit bowed. So I'll draw it. And I'm going to show you arrows in the order that I was actually filling these things in. Okay. And now we have 1, 1. And 4. That's the 2 equals 2. So again, I'm going to trace out in the sort of both direction and put in a few arrows just to show. So we're tracing out here to here.